All right, for those of you that are on Zoom, please say something in the chat. For those of you that are physically present, I'm about to pass around, excuse me, the roll sheet. So we have spent the last couple of lectures laying down groundwork for determining, I guess I should wait until I'm back on Zoom. All right, make sure this is just all people saying that they're here. Yep, all right. So we have spent the last couple of lectures laying down groundwork to look at the frequency response of transistor circuits. As I mentioned the other day, I think it was last Friday, that generally speaking, the response of a transistor amplifier is going to look something like this. So here is our voltage gain measured in decibels. Here is frequency measured in hertz. This could just as easily represent omega since they're the exact same quantity, just related by a factor of 2 pi. And we should see that we have something like this. Bless you. Where this frequency here, I'm going to call it F low. This frequency here is F high, and they represent the 3 decibel or half power cutoff frequencies at both the high part of the frequency response and the low part of the frequency response. And we can break our frequency response up into then 3 portions. We have our low frequency band, where the gain falls due to coupling and bypass capacitors. And so those are the capacitors that we were putting in when we were doing our DC analysis to say short out or bypass the effects of degeneration to increase the gain and things like that, or to decouple our time domain or time varying input from our DC biasing circuit. Here in the middle, we have our mid-band frequencies, where we can say that all capacitors are ignored. And finally, on the right-hand side, we have our high frequency band. Where over here, the gain falls off due to internal capacitances. So hopefully it's fairly obvious, but our transistor amplifiers, their generic frequency response looks like that of a bandpass filter, okay? Where there is a certain range of frequencies called the midband, where we get the DC behavior that we expect, both the small signal DC behavior that we expect, and then outside of that, we are going to see some frequency response issues. So for a general bandpass filter, we can have a transfer function, H of S, which will be the output voltage as a function of S divided by the input voltage as a function of S. And generically, this is going to look like the following relationship. AM, This is what's called the mid-band gain. So this is the gain that we have been calculating up to this point. This is nothing new whatsoever. And then we are going to have poles and zeros. So we could have 1 plus S over omega Z1 for the first zero, 1 plus S over omega Z2 for our second zero, all the way out to 1 plus S over omega Zn for our nth zero. And we're going to have, so those are all our zeros. Our poles will be in the denominator. So we'll have 1 plus S over omega P1 down here, 1 plus S over omega P2, and 1 plus S over omega P sub n. Now, what is interesting is that some of these poles and zeros may be associated with frequencies below the midband, and some of them may be associated with frequencies above the midband, such that we can write our transfer function as AM times F, let's call it low as a function of S, times F high as a function of S. And because we can separate these things, this actually allows us to analyze the circuit only at the low frequency band and only at the high frequency band and only at the mid band. So we can actually work the circuit in 3 different regions of frequency so that we understand how it behaves across all frequencies. So with that in mind, let's look at the frequency response of a common source amplifier. All right, so before I begin here, I want to talk about a little something. I am going to analyze this particular amplifier to death, okay? To introduce all of the different means and shortcuts and stuff like that that we can use to make estimations on the frequency response. So I'm probably going to spend 2 full class periods or so just on this guy, and then all of the other amplifiers, we could use those techniques and get the results in just a couple of seconds. So I'm going to beat this guy to death and then effectively just give you the results of all the other amplifiers because we get them using the exact same techniques. So does that seem like a reasonable approach? All right, because that's what I've got planned. So we're going to start with our low frequency analysis. All right, so let's say that I have the following circuit. And this is going to be a little bit more detailed than what is done in the textbook, which means if you can follow this, the homework and the exam should be a joke. So here's our drain, our gate, our source of transistor M1. We're going to assume that lambda is equal to 0 to make our math much less of a pain in the butt. Here's our resistor R2. Okay. And I'm going to call this guy right here node X. So this is a common source amplifier, but we have also included source degeneration because we know that this provides a more stable DC operating point, and at sufficiently high frequencies, this capacitor CS is going to act like a short circuit, which will short out our degeneration resistor, meaning that it will look like a basic common source amplifier without degeneration at high frequencies, or at really in the mid-band there. So we are going to be analyzing this circuit at low frequencies, where this capacitor CS and this capacitor CN can no longer be treated as short circuits. To analyze this guy, right now, this looks like it could be a bit of a pain in the butt, and you wouldn't be entirely wrong. So what we're going to do is we're going to break things down into manageable parts to kind of simplify what's going on. So for example, I can take this whole input section, everything to the left of that dashed line, and develop a Thevenin equivalent for it. So that would look like this. So I would have input voltage, R sig in series with Cn. Here is R1. Here is R2. And this node right here, where all the capacitor and R1 and R2 are connected, is my node X in my original diagram. And down here is ground in my original diagram. And I could find a Thevenin equivalent voltage, which would be related in some way, shape, or form to our actual applied input voltage. So hopefully everybody can see that I can get here just using very simple voltage division. And so I'm going to see that Vthev is equal to Vn times R1 in parallel with R2 divided by R sig plus 1 over SCN plus R1 in parallel with R2. And if I multiply through by a factor of SCN, I get 1 plus SCN times R sig plus R1 in parallel with R2 in my denominator, and SCN times R1 in parallel with R2 in my numerator. Right? I'm doing that multiplication by SCN now, so that we'll see in a little bit when we develop the transfer function for the whole system. This is actually giving us a 0 and a pole. Yes, thank you. So let me put Vn just right up here. Yeah, sorry, skipping ahead in my head to where we have Vthev over Vn. So yeah. All right, so we know what our Thevenin voltage is going to be in terms of our input voltage. Now we're going to need to know what our Thevenin resistance is. So for our Thevenin resistance, or really impedance, we're going to compute that with our input voltage source turned off. So we're going to have R sig Cn R1 R2 looking in this way, we're going to see some impedance Z Thevenin, and should be fairly easy to see. This is just R1 in parallel with R2 in parallel with the series combination of RSig and CN. Like so. All righty, we can also simplify our degeneration stage. And by that, I mean we can pretty easily see by inspection that between node S and ground, we just have an impedance that is RS in parallel with CS. So looking in here, we're going to find that ZS is RS multiplied by 1 over SCS divided by RS plus 1 over SCS, which is the same as RS divided by 1 plus SCS RS. So I'm going to redraw my circuit now, including those simplifications. Yes. All right. So redrawn, my circuit looks like this. Here is, sorry, did I say RThev or ZThev earlier? ZThev, okay, that's what it should be. And this node right here is node X. So we have simplified our circuit and it now looks like what? Just a very simple common source amplifier that happens to have some resistance attached to the gate, and it also has degeneration. So I can say that my transfer function, H of S, is going to be V out of S over Vx of S multiplied by Vx over Vthev, and then multiply that by Vthev over Vn. So that overall, I get V out over Vn, which is exactly the transfer function that I'm looking for. So V out over Vx is easy because we've already analyzed this circuit way back in 335. We don't need to do any extra work whatsoever. So this is just going to be negative GM RD divided by 1 plus GM ZS. So instead of having RS, we now have that impedance ZS because the capacitor matters. What about our relationship between Vx and Vthev? Exactly right. They are identical. because we know that no current can flow into the open circuit capacitance seen between the gate and the source. So Vx is exactly equal to V set Thev. So our transfer function there is just 1. And V Thev over Vn is that relationship that we got earlier. So if I substitute that in, I'm going to have 1 plus S Cn R sig plus R1 in parallel with R2 divided by S Cn, or excuse me, in the numerator, SCN R1 in parallel with R2. And if I substitute in, I'm going to rewrite this slightly. I'm going to have negative GM RD multiplied by a factor of 1 over 1 plus GM RS divided by 1 plus SCS RS. So all I've done there is just substituted in ZS, because we know that ZS is RS over 1 plus SCS RS. Take this guy. So my second term is still going to be the same. 1 plus SCN R sig plus R1 in parallel with R2. SCN R1 in parallel with R2. And lastly, then I'm going to multiply by a factor of 1 plus SCS RS in both the numerator and the denominator, which is going to give me negative GM RD times 1 plus GM RS plus SCS RS, and then 1 plus SCS RS up here. And then that same factor, 1 plus SCN R sig plus R1 in parallel with R2. SCN R1 in parallel with R2, like so. I have expressed the transfer function in this way because this is exactly of the form that I talked about earlier. Negative GM RD is my mid-band gain. Then I have my zeros on top and my poles on bottom. And so from that, I can see that the magnitude of my pole frequencies, I'm going to have 1 at 1 over Cn times R sig plus R1 in parallel with R2. I'm just doing that by inspection based on my previous definition. I'm going to have a second pole, omega P2, at 1 plus GM RS divided by CS RS. I'm going to have a 0. WZ1 is going to be at 1 over CS RS. And finally, I'm going to have a 0 at 0. Okay. See if anybody's asking a question or if those are all just people saying here. Okay. So I have all these poles and all these zeros, so I can put together a simple Bode plot that would be an estimation of what my frequency response should look like. So here's the magnitude of my voltage gain measured in decibels. And let's see. So every time I have a pole, I should be expecting a roll off of negative 20 decibels per decade. And every time I have a zero, I should see an increase of positive 20 decibels per decade. So I am going to start over here and say that this region is where my midband starts. So I have a gain of GM/RD at omega P. I see that pole, so I'm going to start to fall. At omega Z1, I see a zero, so it flattens out for a bit. At omega P1, I see another pole, so it's going to start to decay, like so. And this value right here is GM/RD over 1 plus GM/RS, where I have made some assumptions here, so let me state what those are. My input capacitance Cn is much greater than my degeneration capacitance Cs, and my input resistance R_sig plus R1 in parallel with R2 is much greater than my degeneration resistance R_s. So effectively, we should see the lowest frequency pole at the highest value capacitance. But it does depend on the resistance as well. So what I have done is I modeled this circuit in LT Spice using specific values, okay? And so our drawing actually seems pretty reasonable. Obviously, it's not going to be a perfectly exact thing as a Bode plot because Bode plots have sharp corners, and these things roll off. And we have not calculated the exact frequency values that we would expect for those poles and zeros. But we do have some midband gain. We have a pole, so it starts to fall. We have a zero, so it starts to flatten out. We have another pole, so it falls down, and it's going to continue falling until we reach a frequency of 0 hertz, which is where we have our last zero. And again, that makes perfect sense because that's the whole purpose of that input capacitor, is to decouple the AC signals from the DC signals. Okay. So using these values, R1 is 8 kilo ohms, well, I'll draw it. But using these values, let's estimate where our poles should be based on our formulas. So if we have the following circuit, $8 kilo ohm resistor there, 2 kilo ohm resistor here. There's our input voltage, 100 nanofarads. 2 kilo ohm resistor here. We're taking our output, the out. Here's our transistor M1. 100 ohms here. 10 nanofarad here. We know that mu n C ox is 200 microamps per volt squared. That's what I use in my simulation. W over L is 15 over 1. Lambda is equal to 0. And the DC operating point for this guy is then somewhere close to 35 microamps based on how I've got this guy biased and all that jazz. So, yes. So for this particular example, let's look. I'm not using one, so we would just set R sig is equal to 0. That's it in our calculations, right? It's not, I mean, it is definitely going to play a role in the location of the poles and zeros. The reason why I did this is your project one with slightly different values, and I ignored the output because we would actually see, since there was a capacitor and a resistor at your output node as well, that would have introduced most likely a third pole. We can loosely say that everywhere that we have a capacitor, every location in our circuit that we have a capacitor should contribute a pole if and only if the locations of those poles are far away from each other. Meaning, if the capacitors don't interact with each other, we can see that. We'll see when we look at the high frequency analysis where there is capacitor interaction because of a Miller capacitance between the gate and the drain, that we're still only going to look like we have two poles even though there's more than two capacitors. But anyway, I just used this where we had no R sig because it should be largely familiar to you guys since you did it as a project. When we look at the high frequency response, I'm going to have to include some signal resistance. Otherwise, it forces one of my poles to go to infinity. So, all right. But good question. All right. So based on these values, we know what our poles should be. So really the only piece of information that we are missing is GM. So we can calculate that guy real quick. So GM is going to be 2 times mu n C ox times W over L times ID. This whole thing, the square root, which would give us a value of 458.258 microamps per volt. Bless you. And from this, the frequency of pole 1, so that's the guy, let's see. So that's just going to be one over 2 pi Cn R1 in parallel with R2 because R sig is 0, so that's why we're getting rid of the R sig there. And so this is going to give us 1 over 2 pi times 10 nanofarads. Let's see, 8 in parallel with 2 is 1.6 kilo ohms. And so we get a frequency of 994.718 hertz. So that's where one of our poles is. Our second pole is at 1 plus GMRS all over 2 pi CSRS. So that is going to be 1 plus this 458.258 microamps per volt times 100 ohms times 2 pi times 10 nanofarads times 100 ohms, and we get 166.0 0.448 kilohertz there. The frequency of our 0, let's see, don't remember that one off the top of my head, 1 over CSRS, all right. 2 pi CSRS looks like 2 pi times 10 nanofarads times 100 ohms down here. 1 up here gives me a frequency of 159.155 kilohertz. And obviously the frequency of our second 0 is 0. So let's see how reasonable of an estimation this is giving us, right? So we're looking for a pole at roughly 1 kilohertz and a pole at roughly 166 kilohertz and a 0 at 160 kilohertz or so. Yes. All right. So 166 kilohertz would be somewhere around here. So we are seeing some roll off in that region, so that seems reasonable. And then we see that pretty shortly after that point, it starts to flatten out. That's from the contribution of our pole. At about 1 kilohertz, we see that this slope is getting very, very steep. So we're looking at, let's see, it should be minus 3 dB. So this is minus 6, so minus 3.6. So yeah, so somewhere around here, we do see that action, but this guy is looking a lot steeper. We can actually back this guy out a little bit. So let me change my simulation from 1 kilohertz to 1 hertz. And we can much more easily see that that pole at 1K, but we're effectively losing looking out at our higher frequency pole. And it's because that 0 occurs so close in frequency that it's a dip and it immediately flattens out. So we have what we would expect, a high pass filter when we're looking at this guy for low frequencies, right? So we should see that when our frequency is very low, these capacitors start to look like open circuits, or these capacitors look like open circuits, and the impedance of this guy is going to get smaller and smaller and smaller more quickly than the impedance of this guy because it has a higher capacitor value. Let me no, I'll change this. It's the phase information is what's screwing this up. So effectively, what we've got is way over here on the left is Cn's impedance decreasing towards short circuit. Then this region is where Cn looks like a short circuit, but Cs doesn't look like a short circuit. So we have degeneration. This region is when Cs's impedance starts to decrease. And this region is where both Cn and Cs look like short circuits, and we've reached the midband. Nathan, what's up?
So the poles are where it sharply turns.
Right.
And the zeros is the frequency where it goes flat.
So everywhere we see a pole, we should see a slope of negative 20 decibels per decade. Everywhere we see a 0, we should see a slope of positive 20 decibels per decade. So here, where it's turning down, this is negative 20 decibels per decade. Then when we see that 0, we add positive 20 decibels per decade to that slope, giving us a 0, making it completely flatten out until we see that other pole where it rolls off. So that's why large picture, this thing is looking like a first order high pass filter, and it's because one of those poles cancels out, or that zero cancels out the effect of one of those poles effectively. All right, so this analysis, pretty easy. Now, one thing that I want to point out here is that a lot of times we are not going to care exactly what everything does below the midband. We really just kind of want to know where the midband starts, and later on when we're doing our high frequency analysis, where the midband ends, so that we know that our amplifier is amplifying signals of the correct frequency. So what we're about to do is introduce a method called the short circuit time constant method, which will allow us to get an estimate of where the midband starts. So effectively, this is an estimate of where F low is in our original bandpass filter representation of what's going on.
And the quarter going midband, is that where it cancels each other out?
The midband is where our gain is constant, has a constant value. Yeah. So the midband, we should expecting it starting at somewhere close to 166 kilohertz, which is our highest frequency pole. Our highest frequency, low frequency analysis pole, if that makes any sense. Okay. All right, so draw a line under this guy. All right. So short circuit time constant estimation. And this is only valid at low frequencies. At high frequencies, we have what's called the open circuit time constant estimation. So the short circuit time constant estimation in principle just says that we are going to be looking at our circuit with only one capacitor on and our input turned off, and see what the effectively what resistance each capacitor sees to develop a time constant for each capacitor. Okay. So I know that sounds like a bit of gobbledygook, but it'll be a little bit easier to understand in a moment. Ultimately, we will find that an estimation of omega low can be given if we do the following operation. So if we add up the reciprocals of the time constants, this is going to give us an estimation of where our midband begins. So this is something, again, that you would do if you don't really care about what it's doing at low frequencies. You just want to know a rough estimate of where your amplifier starts behaving as a simple small signal amplifier. You raising your hand, Sam? What's up?
For low frequencies, is that relative to the amplifier?
Relative to the midband. So everything below F low is low frequency. Everything above F high is high frequency. Everything in the middle is the midband. So we're going to do, again, a similar thing when we're looking at the high frequency capacitances. So when I say low frequencies here, what I really mean is this can only be applied to the coupling capacitors and the bypass capacitors and stuff like that, which is what we've been looking at. All right, so we have our common source amplifier. Let me just redraw it just for the sake of argument. Here's RD. Here's V out. RS, CS, sorry, R1 should be up here, R2 should be here. Cin, R sig, Vn, VDD. Okay, I believe I accurately redrew everything. All right, so for this method, we're going to start by looking at what our input capacitance Cin sees when we short circuit our capacitor Cs. And we're also shorting our input signal to ground. So it's effectively, we're looking for a Thevenin equivalent resistance with respect to each of those capacitors. So our capacitor Cin sees something like this. So we have, here is Cin. So we have our signal over here. Our input is grounded. Small signal, we have R1 in parallel with R2. Here's our transistor, where since CS is grounded, that means our source effectively just sees a short circuit to ground. Here's GM VGS. Here is RD. So hopefully by inspection, we can see what resistance our capacitor Cin sees. So somebody give me a stab of what it's going to be. Close, but not quite. Let me make it a little bit more obvious. If I take my capacitor out and I'm looking in through those terminals, I see R sig in series with R1 in parallel with R2, right? Everybody okay with that? So from that, our time constant, and I'm just going to call it tau n, is going to be Cn times R sig plus R1 in parallel with R2. Our capacitor Cs sees something a little bit more difficult. So here's R sig connected to ground. Our capacitor Cn is now short circuited. So here we have R1 in parallel with R2. GM VGS. Here is RD. Here's RS. Here's CS. So this one is, like I said, going to be a little bit more difficult. So I just want you to remember that what we're ultimately trying to do is to determine the Thevenin equivalent resistance as seen by this capacitor. So what I'm going to do to simplify this further so that I can accurately determine the resistance seen by this guy is pluck this guy out and apply a test source method to determine the resistance, because I have this pesky dependent source in there that's messing things up and allowing me to not directly see what's going on. So if I take my capacitor out, I'm just going to draw the nodes where my capacitor was. And this bottom node is ground, and this top node was my source, right? I have between my source and ground, for sure, my resistance RS. And then I also have between my source and ground a current source GM VGS in series with my resistance RD. And my current is flowing from the resistor RD towards my source. So it should have this direction. So where is my voltage VGS going to go? Let's think about that. Yeah. So the negative polarity terminal is tied to my source. And the positive polarity terminal, it should be pretty obvious, is tied to ground because there's no current flowing through any of this parallel resistor combination there, because there's no independent source pushing current through it. So here I have plus VGS, and using the test source method, I'm going to apply some voltage Vx here and measure the current Ix, and the ratio of those two guys gives me my resistance. So just doing good old Ohm's law, or excuse me, KCL, I see that Ix is flowing into the source node, GM VGS is flowing into the source node, and Vx divided by Rs is flowing out of the source. I can see by inspection that Vx is equal to negative VGS. So this gives me Ix minus GM Vx is equal to Vx over Rs, which tells me that Ix is equal to Vx times 1 over Rs plus GM, meaning that the resistance Req seen is simply Rs in parallel with 1 over GM. From this, my time constant, tau S, is CS times Rs in parallel with 1 over GM. And from this, overall, we can see then that omega low is 1 over Cn R sig plus R1 in parallel with R2 plus 1 over CS times RS in parallel with 1 over GM. And if we plug in our numbers for these values, we find that our estimate for our low frequency is 167.442 kilohertz, which is actually pretty darn close to where the midband begins. We saw that it began at 166 and change kilohertz. So this is a fairly good estimation. All right. Which one is harder and which one is easier is entirely up to you guys. I'm just trying to provide you with options. I do want to point out here, though, this doesn't tell us anything about zeros in our system at all, and it doesn't tell us anything about other poles. All it is doing is giving us an estimation of where the midband begins, which may be all you need as a designer, because you, generally speaking, if you want an amplifier to work a certain way, you really don't care how it's going to work in low frequencies or how it's going to work effectively outside of your frequency range of interest. So this is giving you one constraint on your frequency range of interest and how to design towards that. All right, so we have 20 minutes left. Okay, we're going to start high frequency analysis then. So at high frequencies, all of those coupling and bypass capacitors are assumed to be short circuits. And now we are running into the problem where we have internal capacitances of the transistor that are going to mess things up. So if I redraw my circuit, where I have my, what am I talking about here? Where I have my bypass and coupling capacitors assumed to be short circuits, I'm going to have something like this. Oops, that's not what I'm supposed to do. Here's RD, here's R1, here's R2. I am intentionally putting in a signal resistance here as well, like we did before. Here is V out, okay? So at high frequencies, we should see the internal capacitances of the transistor come into play. So let's see. If this is my drain, gate, and source, we should have some capacitance here, CGD. We should have some capacitance here, CGS. We should have some capacitance here, CSB. Notice CSB is grounded on both sides, so we're going to throw it away, which is why I fully do not understand why the textbook keeps it, because we throw it away every damn time, but whatever. Or at least for all of these single stage amplifiers. And then we also have a capacitance between our drain and our body. So I'm going to tuck that guy in right here. CDB. Okay. So this is what our high frequency model for our common source amplifier is going to be. And up here, we obviously have VDD. So I'm going to go ahead and mention that that guy is completely useless. And I'm going to redraw this guy in a more small signal-y way. What's up? All right. So we are operating at a frequency where CS is doing effectively nothing. Now let me prove this to you. Let me kill this guy. Save my changes now. Yeah, so because it is a short circuit, you can ignore the resistor, but I drew our circuit with our AC coupling capacitors, our bypass capacitor, as well as our high frequency capacitances, okay? So we know that when our sig is very close to 0, because that's what we did earlier. So I'm just going to put this as 1 micro ohm, which is pretty dang close to 0 in comparison to everything else. And I simulate this guy. Oh, I need to back this guy off actually, because I'm starting it at 1 mega ohm. So let's start it at 1 kilohertz. And let me make it not blue so that you guys can see what the hell's going on. All right. So this region over here around 1 kilohertz is where our C-in capacitor is going from an open circuit to a short circuit. Then we have that pole that we talked about earlier. This is where our capacitor CS is going from an open circuit to a short circuit. In this range, all of our internal capacitances look like open circuits. This is the region where all of those internal capacitances start going from open circuit to short circuit until it finally rolls off. So, because we are beyond the midband, our capacitor CS looks like a short, which shorts out RS, which is why RS isn't showing up in our model. Does that make sense? Okay. All right. Okay, so I'm going to redraw this thing, setting all of my AC grounds up and stuff like that, so that I can work on my simplification a little bit. So, for example, this would look like this. Here is our sig. Here's R1 in parallel with R2. Now I'll see my capacitor CGS between my gate and ground, bless you. From here, there's my source. Here's my drain. I'm going to have that capacitor CGD is going to show up here. Here is RD. Here is CDB. And here is V out. Okay. Excuse me. So, a couple of things. I can see that RD and CDB are in parallel, so I could combine them. I'm not going to, but I'm going to use this guy to get a Thevenin equivalent resistance and all that kind of good stuff to see what's exactly going on. So in this case, excuse me, my node X is right here, and I am going to, I can see that R1 in parallel with R2 is in parallel with CGS, but I'm not going to sweep that into my Thevenin equivalent. It'll make the pole stand out more if I don't do it, okay? So I could replace this guy with a Thevenin equivalent voltage that is going to be what? Just by inspection here. So I'm going to apply V Thevenin at node X, which is the gate terminal of my thing. So if I disconnect everything to the right of this dashed line, what's my open circuit voltage going to be? It's a voltage divider, right? So VThev is just going to be Vn times R1 in parallel with R2 over R sig plus R1 in parallel with R2. Excuse me. And while I'm at it, I can say that Rthev, and it's just going to be a resistance this time, is going to be R sig in parallel with R1 in parallel with R2. Everybody okay with excuse me, if we were doing this with a, what can we call it? A BJT, we could do a very similar thing, and then everything past this point is exactly the exact same analysis. All right, so, excuse me. I am going to now redraw this guy in a more conventional small signal model fashion, just based on this one simplification. So here is where I would be applying my Thevenin voltage. Here is my Thevenin resistance, R Thev. This is node X. This is CGS. GM VGS, where VGS is the voltage drop over that capacitor. Excuse me, sorry. Here is my source, so that's at ground. In parallel with my current source, I have some resistance RD. In parallel with that, I have, sorry, this should be a capacitance. CDB. Here's my output node, V out, like so. And the only thing that I'm missing then is this capacitor between node X and what I'm now going to call node Y, which is my output node, and this guy is CGD. All right, so it should be fairly obvious that we could use the Miller effect to split this guy up, and we're absolutely going to do that after we analyze it directly to see how good of an estimation the Miller effect gives us, right? Because we need to know whether or not it's actually useful in these types of circuits. So to analyze this guy directly, I am going to have to do Kirchhoff's current law at node X, KCL at node Y, and then lots of substitutions to figure out what the transfer function of this guy is. I'm going to be skipping several steps because it's just purely terrifying algebra. I did it to make sure the book wasn't pulling my leg, but it's not, so you guys don't need to suffer through it. So with that in mind, if we do KCL at node X, we have a current of Vthev minus Vx divided by Rthev flowing in. We have a current of Vy minus Vx, and this is divided by 1 over S CGD, which is the same as multiplying by S CGD. And this is going to be equal to the current flowing down through capacitor CGS. And so that's going to give me S CGS Vx. So what I am going to do, let's see. No, because I'm not going to do all these terrible substitutions. We're going to skip that. If I do KCL at Y, I'm going to have SCGD Vy minus Vx. So that's my current flowing to the left. I'm going to have GM VGS, which in this case VGS is just Vx as a nodal voltage. Plus Vy over Rd plus SCdB times Vy is equal to 0. Then skipping steps, I'm just going to explain what would happen. This guy only has Vx and Vy in it, so I can write Vy in terms of Vx, substitute into here, where I would replace Vx with my rearrangement of this guy, and that will give me a relationship with only having Vy and Thevenin, where Vy is my output voltage and Thevenin is directly related to my input voltage, allowing me to write the following terrifying transfer function. Let me skip ahead in my notes. All right, so several steps of algebra later, Vy over Thevenin is going to be S squared Rd Rthev CGD CGS plus CDB CGD plus CDB CGS plus S times 1 plus GM RD CGD Rthev plus RD CGD plus CDB plus Rthev CGS, close that bracket, plus 1. That's my denominator. Told you guys you don't want to do this algebra. You can. It's not hard. It's just wildly tedious. And in my numerator, I am going to have negative GM plus SCGD, this whole thing multiplied by RD. Now notice, just real quick here, this is Vy over Vthev, so this whole thing would actually be multiplied by that transfer function between Vthev and Vn as well. So this is a good stopping point where we have just reached a terrifying result, okay? So we're going to talk about how to make this terrifying result useful, and then talk about 2 other ways to get to effectively this point way, way faster so that you should never, ever directly analyze a circuit again. All right, so that's enough out of me for today. You should be able to do at least a couple of your homework problems now. So, all right, I'm going to make sure that I save this so that we can restart on this one specifically.